Hey everybody, welcome to, what are we on here? Class number 4. So today we're going to be talking about pH, pOH, pKw, and what they are, how they're related to hydronium and hydroxide and the Kw, and how they fit in mathematically, and how they're going to fit into your previous knowledge as well, like coming out of grade 10. You knew a pH scale. Neutral was 7, you go acidic, it goes below 7, and every time you go down 1 on the pH scale, it becomes 10 times more acidic, and it's basic on the above 7, and it becomes 10 times more basic. Well, what does all that mean? Like, mathematically, you never figured it out. No one ever told you, because one, you didn't know about molarity, and two, you didn't know about hydronium and all of that stuff we've been doing over the last 3 classes. So, today, we're going to get into the mathematics of pH to hydronium. The math is exactly the same for pOH and hydroxide. So pOH and hydroxide are connected to each other. pH and hydronium are connected to each other. And pKw is connected to Kw. So you can kind of tell that anytime you put that little small p in front of something, you're talking about some mathematical function of. So pH is the mathematical function of something to do with hydrogen, and pOH is the mathematical function, something to do with hydroxide, and same with Kw. So the mathematical function's the same for all 3 of those things. So let's start right at the beginning here with pH to hydronium, and kind of back and forth, You're converting back and forth between the 2 things. We'll do pOH and hydroxide as well. There's kind of 2 things you should be able to walk out of here with. Number 1, you should be able to quickly, rapidly convert back and forth between any 2 values. So if I give you hydronium, you should be able to get pH. If I give you pOH, you should be able to get hydroxide fairly easily. So it's just using a calculator. You don't have to be able to do it in your head. It's just pulling out the calculator, doing the right computation. The second thing that's a little bit new here is the sig fig rule. And I know some teachers, some professors, they don't really necessarily care a whole ton about the sig fig rules. I try to be a bit of a stickler on the sig fig rule or sig fig rules. So there's a new rule that's involved here with pH and pOH and pKw. So when I'll introduce that rule to you, I'll try and explain some of the logic behind that rule so it sticks in your head, and it's not just some kind of random thing that you have to memorize. It actually has rhyme and reason to it, as sig figs actually do. They're not just a nuisance to make your life complicated. They actually have experimental purpose to them. Okay, so first of all, pH and hydronium. So I'll just start with that one. So couple of things that we need to start with, and I'll just write them down and we'll kind of start there. So the very first thing is a formula. Okay, so the relationship mathematically between pH and hydronium. So the relationship is this. The pH of a solution, of any solution, if you're going to say the pH of this solution is. Well, the pH is related to how much hydronium is there. Hydronium. Not acid, not HA, if you recall from a couple of classes ago where I used the generic term HA, which is the acid. We're talking about the hydronium, how much hydronium that acid makes. And we're not talking about hydroxide, even though in every water-based solution there's going to be some hydroxide. pH is referring to hydronium and only hydronium. That's it. Nothing else. So if you know a pH, you know the hydronium. You can get other values from the pH and from the hydronium, but you're not getting them directly. Okay, so that's kind of a very important part to get. So the relationship is between pH and hydronium only. The relationship is this. So hydronium is measured in molarity, and it's measured in molarities that have factors of 10. And you know that because you look at the scientific notations, and it's something times 10 to the power of, and they're, anywhere from 2 all the way down to -14, -15. Like, you're going to see these ranging values all the time, but they're by factors of 10. And because they're ranging in factors of 10, you can use a logarithmic scale, which a logarithmic scale is actually based on base 10, log base 10. So for those of you with your Math 12, you'll kind of know what I'm talking about there. So logs are a base 10 concept. So they're a way of having a numerical value instead of using the exponential form of 10 to the power of. The pOH, or the logarithmic form, is just what is the power. That's all it is, okay? Kind of knowing that it's base 10. So we're going to be using a logarithmic scale. So the pH is the negative log. Okay, so there's a negative sign out in front, and there's a reason for that. It's the exponents tend to be negative. It's usually say 5.4 times 10 to the negative something. That's typically what you're going to have. You're like 10 to the negative 7 in water at 25 degrees. Hydronium is 1 times 10 to the negative 7. And so since that exponent is negative, to have it as a scale that we can all talk about, we take the value you're going to get, that exponent value you're going to get, multiply it by -1, and therefore it comes up to being positive. So when we say a pH of 7, really what you're talking about is you're talking about something 10 to the power of -7 rather than +7. Okay, so that's where the negative sign is coming from. Kind of makes it a little bit more usable for our brains. So we're taking the negative log of the hydronium concentration. But if you know the hydronium concentration and you know where the log button is on your calculator, you can get a pH. It's that simple if you can find it on your calculator. Now the reverse, what if, okay, so that's, if you know the hydronium and you want to know the pH, you take the negative log of the hydronium concentration, you get the pH. Well, what if you know the pH of a solution and you want to know the hydronium? Like, what is it in the reverse? So in the reverse, the hydronium, and I don't really feel like going into the math behind it all, but again, like I said, you're talking about a base 10, right? And the pH is the exponent of that base 10. So the math that's involved, the little formula that you're going to use, kind of plays that out. So the hydronium concentration is going to be 10 to the power of whatever the pH says, negative. So 10 to the power of negative something. So if you had a solution that was pH of 5, the hydronium concentration is 10 to the power of -5. And that's just what it is in molarity. Okay, so those two little formulas right there, no one's going to give them to you. You have to have them memorized. Okay, so you just have to know them. Again, the acid-base unit is so big and you're going to be doing this so often that this is just, like, you're not even going to really think about it. You're going to be given a pH and you're not even going to think twice. You'll go 10 to the power of negative whatever it is, and you'll get that value. Okay, so we're going to use these things. If we were talking about pOH, the concept, the actual mathematical relationship is exactly the same. So pOH the math is the same, we're just talking about something different. So instead of talking about the hydrogen, pH, we're talking about the hydroxide, pOH. So everything that's hydronium in here is going to be replaced with hydroxide. Same concept though. So the pOH is going to equal negative log of the hydroxide concentration. And again, if you happen to know the pOH and you want to know what the hydroxide is, going in the reverse direction, the hydroxide concentration will be 10 to the power of the negative pOH. Okay, so those little things kind of stick in your head. You'll use those conversions back and forth all the time. Okay, so how does it play out? Like, how do you go about doing this thing? So we'll do a couple, and once you get it, you'll practice it. I'm sure your teachers are going to give you lots of homework. I know I do. I do a whole bunch of things. Is just kind of knowing where everything is on your calculator. And once you've got it, then you don't really need to practice it anymore because it'll go like that. Okay, so get it, and then move on. Don't spend too much time doing it. One thing that might throw you for a loop is when I start talking about the sig figs, and there's some kind of weird things that happen. And sometimes you also get some things that maybe you didn't know from your previous knowledge, and you go, oh, that's kind of interesting. I guess I better put that in the back of my head just in case it comes up in some calculation or some conversation or some lab or something like that. And it seems unusual, but you'll see that it's not that unusual. So let's keep these things in mind, okay? So take a snapshot in your head of that. Okay, so maybe you've heard of a pH meter. At some point you've heard of a pH meter. pH meter is, it's a funky little device, and there's really cheap ones, the little handheld guys that may be used in Science 10 or something like that. You dip it into a solution, you press the button, and it gives you a digital reading of what the pH is. Now, I say they're the cheap version. They're not that cheap, so don't just kind of fool around with them because, what the hell. They actually have very sensitive materials in them. They actually have, if you look really closely at them, they have a glass ball down at the bottom of the pH meter, and inside of that glass ball is exactly 1 molar solution of hydronium. So that's it's fairly concentrated, but what it does is the pH meter is measuring the difference between what's inside of the ball, the glass ball, and what's outside of the glass ball. And that difference in concentration, a little bit for the biology people out there, that difference in concentration is a gradient, and it actually creates an electrical gradient between the two. So the bigger the difference between 1 molar and what's outside, the greater the electrical potential. And so the meter is designed, it's calibrated to be able to read what that electrical potential is. So that little glass ball that's filled with a solution is very sensitive. If you break it, obviously you've ruined the whole thing. Like, you can't fix it. And even if you do any kind of damage to it, or you ruin kind of the porous nature of the glass or whatever you do, you've ruined the pH meter. So be very understanding of that. So there's those little handheld guys, and they're fairly quick and easy, and they're not super analytical and technical. And then you'll have the really more analytical ones that kind of sit on the lab countertop, and then you put the probe in, and it's got the same concept. It's got the glass ball that's filled with 1 molar hydronium, and it measures the electrical potential between the solution you put it in and inside the ball. Same concept. It's a much more technical piece of equipment. So we do have pH meters. You dip them in and they just tell you what the pH is. It measures that right off the bat. Now that you're about to learn, so here's the pH, here's what the hydronium is as a result of that. So that's kind of how we do it. The pH meter is kind of our way of doing it. There's other ways as well in terms of titration and things of that nature, knowing what you've got and all that stuff, but pH meters are pretty straightforward. They let you know these things. So let's say I have a solution, and in that solution, a solution at 25 degrees Celsius, and I'm always going to say at 25 degrees Celsius. I'm going to try and get you to recognize that 25 degrees Celsius is really critical, because we're going to start using numbers, constants that are only applicable at 25 degrees Celsius. So a solution at 25 degrees Celsius has hydronium concentration equal to, let's go with 9.2 times 10 to the negative 4 molar. Now we're gonna do 3 of them. The first one is this one. The second one, I'm gonna change that value. Okay, and I'm gonna change it to a really small number. And then the third one's gonna be a weirdo one that I'm going to give to you. And what I want to do is obviously we'll go through the mechanics of it. The mechanics are pretty straightforward. But while we're doing this, I'm going to give you the sig fig rule as well. Okay, so that you can see what's going on here. Okay, so let's just stop for a second. Let's use our logic and what do we know theoretically here. So water at 25 degrees, if it was distilled, the hydronium concentration would be 1 times 10 to the negative 7, the square root of kW. it would also equal the hydroxide. They'd both be 1 times 10 to the negative 7. It's neutral, that's why they're equal. So this solution that I've given you here has hydronium of 9.2 times 10 to the negative 4. That value is bigger than 1 times 10 to the negative 7, which is telling me that at 25 degrees, if this is the case, this solution is acidic because the hydronium has gone higher than what it was when it was distilled. So I should, A, anticipate I'm going to have a pH in my answer. I'm going to have a pH less than 7 because at 25 degrees, 7 is neutral. That is true. And if I was asked, what's the hydroxide concentration? I would anticipate that the hydroxide concentration is smaller than 1 times 10 to the negative 7. Remember last class where if one goes up, the other has to go down so that they still multiply back to kW. So I'm kind of thinking all of those things in my head. So I haven't even really asked you a question yet. I've just kind of told you this concept. This solution has a hydronium of this, 9.2 times 10 to the negative 4 molar. So question would be, what is its pH? Okay, now I could ask you a whole bunch of other questions, and you will get these questions later on and make it a little more complicated. What is its pOH? What is the hydroxide concentration? What is the value of kW? Right? There's a whole bunch of things that I could ask. I've given you hydronium, which means that if I give you the hydronium concentration, you can go directly from hydronium concentration to pH. Like that's going to be a direct connection using your little mathematical formula. pH is the negative log of the hydronium concentration. So that's one thing that you can do, which for this question, that's what we're going to do. But you can also go directly from hydronium concentration to hydroxide concentration using the K expression for water. You know that Kw equals hydronium times hydroxide. You know Kw because it's at 25 degrees. You know hydronium because I just gave it to you in the question. Therefore, you can calculate hydroxide that way. So there are two things that you can do directly. Have that in your mind. pOH was not one of those. pOH you can get to indirectly, as we're going to see, number 2 on our things to do today is that indirect kind of connection between things. Okay, so I've asked you a direct question. What is the pH from the hydronium? Sure, those two are related in a little perfect mathematical formula. So pH equals the negative log of the hydronium. So I'm going to plug in what I know. I don't know pH. I do know the hydronium. So the pH is going to equal something. Okay, so I pull out my calculator and I'm going to need to put on my glasses so I can actually see my calculator. Okay, so I'm taking the negative log of 9.2 times 10 to the negative 4, where's my bracket? Equals. Okay, so I'm going to give you the whole long decimal that it gave me. So it gave me 3.036212. Okay, that's enough. Okay, so it gave me that. So what do I do with that? Okay, one, does that make sense? Well, it's below 7, so it makes sense. Right, pH of 3-ish is acidic, and we already figured out that this should be acidic because it was below 10 to the negative 7. Sorry, the hydronium was above 10 to the negative 7, and so therefore it should be acidic. Okay, cool. The other thing that you should be paying attention to is this, that the exponent right here, that negative 4 on the molarity, gives you some indication. It should be around pH of 4, right? 9.2 times 10 to the negative 4. 9.2 is almost up to 1 times 10 to the negative 3. Right? Like it's almost there. It's It's closer to 1 times 10 to the negative 3 than it is 1 times 10 to the negative 4. So you should be able to anticipate that this guy should be between pH of 3 and pH of 4, knowing that we're talking about the exponent on the 10, between 3 and 4. But it's closer to the 3 than it is to the 4, because 9.2 is almost up to that 1 times 10 to the negative 3. So if that's the case, I should be able to, before I even hit the calculator, I should be able to figure out, generally speaking, where it's going to be. You can use your logic to kind of check yourself. So if you come up with an answer and it says pH is 8, you go, oh, wait a minute, that can't be right. It's supposed to be acidic. It's supposed to be less than 7. So 8's wrong. If you came up with an answer of 2, well, no, because the exponent is negative 4. So pH of 4, and then it should be within, like it's on its way to 3. So it should be between 3 and 4 somewhere. So 2 is off. So you can use your mathematical logic to anticipate what's right and what's wrong when you finally come up with an answer. Okay, so this guy's got to be in the neighborhood. 3.036212 is in the neighborhood. So I'm pretty happy with that value. Okay, now sig figs. So sig figs are when you're talking about a pH. Okay, so only when you're talking about a pH. This isn't just for this whole unit. When you're talking about a molarity, what you knew previously is correct. So on this molarity that's right here, okay, in the original question, 9.2 times 10 to the negative 4 molar. 9.2 is how many sig figs it has. The 9 and the 2 are both significant. It has 2 sig figs. That's what that value has. So I'm going to write that down. So this guy right there has 2 sig figs. It's a molarity. It's what you did for grade 11 and up to this point in grade 12. We convert it to a pH. And so you kind of look at it and you go, well, okay, 3.0. So 3.0 looks like 2 sig figs, correct? Wrong. It's not 2 sig figs. The number that's before the decimal, okay, so the 3 in this case, so that 3 right there, the 3 that comes before the decimal is related to the exponent. The numbers after the decimal are related to this part right here, not the exponent. The exponent on the 10 doesn't have sig figs. It's a whole number. It's round. It's a 4. It's got infinite sig figs. So that thing doesn't even count. So the 3 isn't really involved in sig figging this thing. It doesn't have anything to do with it. So all we care about are the digits after the decimal. It's the digits that count. No matter what those digits are, they always count. Okay, I'll give you a little example just to kind of show you. If I had a pH equaled to 0.000002, if I had that written down on a piece of paper, you might say, kind of in your old sig fig brain, you'd go, well, all the leading zeros before you get to that 2, they're just filling place value. They're not actually significant. Well, that you have to get out of your head when you're talking about pHs. When you're talking about pHs, everything after the decimal, no matter what they are, counts as a significant figure. Which means that counts, so does that, so does that, so does that, so does that, and so does that. 1, 2, 3, 4, 5, 6. Count. This guy does not count. Okay, so out in front doesn't count. Doesn't matter what it is. It doesn't count. What happens after the decimal does count, and doesn't matter what it is, it always counts. Unusual and strange. So this guy right here would have 6 sig figs. That guy has 6 sig figs because there's 6 digits after the decimal, even though 5 of them are zeros. They count. So, having said that, kind of using that theory, that pHs and pOHs, all the numbers after the decimal are sig figs. Whatever's in front of the decimal is never a sig fig. Doesn't matter what it is. if I look back at my answer here then, and I say to myself, okay, so I've got a pH of 3.036212, but I'm using a concentration that had 2 sig figs. So in my answer, I'm allowed to get 2 sig figs. So what are the sig figs that count? The 3 does not count. The 3 doesn't count. So this guy counts. This guy counts. Which means I need to round this thing off. So it's 3.0, either 3 or 4. It's either saying it's 3 or going up to a 4. So you look at the one to the right of it. So the 6 means it goes up. You round it up. So this answer to the proper number of sig figs is 3.04. That is a pH of 3.04. It has 2 sig figs. 2, not 3. Okay? So that rule, it'll take you a little while to kind of remember that because it looks weird. So when someone says to you, you've got this pH or this pOH and it gives you a value, and you're going to go, okay, so how many sig figs does that have? How many do I get on my concentration at the end? You know, to stop and remember what that rule is. Okay, so here's the next one. Okay, so I've changed my mind because we did a lot on that one, so I think it's probably fairly clear, and we'll practice this a little bit more. But I'm going to give you one that's kind of a strange one. Okay, so let's say you have a solution at 25 degrees, and the hydronium concentration is 2.00. 2.00, 2 molar hydronium. Now you might say, ooh, that's pretty concentrated. And you'd be right, it is pretty concentrated. So then and the question says, what is its pH? What's the solution's pH? When the hydronium is 2.00. So same thing applies. pH equals negative log of the hydronium. pH equals negative log of 2.00. How many sig figs do I have? 2 counts, the 0 counts, the 0 counts. It's a molarity, it's a concentration, so all the digits kind of follow the same rules that you've always known. It's a concentration. So I have 3 sig figs. So on my answer, I'm going to make sure I have 3 numbers after the decimal, whatever the answer comes out to. So then I take the negative log, of 2. So I pull out my calculator, I put in, you don't really need to put in the 0, 0. You can just go log of 2. You're supposed to know the sig figs. And it comes out to, okay, that's weird. Came out to pH is negative 0.3. Okay, I get 3 sig figs. So 3, 0, 1. After the 1, it goes 0, 2, 9, 9, 9. So because there's a 1 after the 0 on that answer, I keep it as a 0.301. That is 3 sig figs. But it's got a negative sign in front of it. I thought the pH scale went from 0 to 14. No, it doesn't. If you're thinking that, okay, well, that's an impossible value. That's not true, and this is kind of why it is. That value right there. If you have a hydronium of 2, if you know about logs, if you take the log of a number, what you're doing is you're figuring out the exponent, right? So if you have an exponent of 0, 10 to the power of 0, okay, what does that equal? You all know this. You've all done enough math for this. 10 to the power of 0 equals 1. And so if you have a 1 molar hydronium solution, the exponent on the 10 is a 0. So 1 molar hydronium is a pH of 0. Well, 2 molar hydronium is more concentrated than 1 molar hydronium, and so the pH must be more acidic than 0. 1 molar hydronium is 0. More concentrated than 1 molar will give you a negative pH, and yes, you can have those types of solutions where they have negative pHs. And yeah, we're talking it's pretty skookum stuff. So you don't want to be around negative pHs a whole heck of a lot. 1 molar is pretty bad. Negative pHs and greater than 1 molar is really nasty stuff. It'll do a number to you and to the stuff that it comes in contact with. So don't freak out if you get a negative pH. It just means that the hydronium is greater than 1. And if you have a pH of 0, you should know that the pH is 0. Okay? Next question. Let's go the other way. So, if a solution has pOH equal to, let's go with 4.8. What is the hydroxide concentration? Okay, so you've got a solution, measures a pOH of 4.8. pOH, right? So the negative log of the hydroxide concentration. I'm asking you, what is the hydroxide concentration? So there's a direct relationship between pOH going to hydroxide concentration. The relationship is, if you know the pOH, or you know the pH and asking for hydronium, if you know the pOH, then the hydroxide concentration is going to equal 10 to the power of, and you have to know that all a pH and a pOH are, is it's the exponent on the 10 with a negative sign in front of it. So this right there is supposed to be the exponent. So it's negative 4.8. So now on your calculator, now you look for the 10 to the x button, you press the 10 to the x button, you punch in negative 4.8, hit equals, and it will give you the value. So I need my glasses again. Okay, so oftentimes 10 to the x, if you have a log button on your calculator, 10 to the x is oftentimes the inverse function of that log button. So I'm going 10 to the power of negative 4.8. So mine is an inverse. So shift 10 to the power of negative 4.8 equals. And if it hit equals, then on my calculator I've got, typically in scientific notation, because you're going to generally get fairly small numbers, sometimes it won't. So I've got, again, the hydroxide concentration. I'll put the whole, or a lot of digits here, 1.5848 I'll go with the 9 times 10 to the negative 5. Okay, so that's what my calculator is saying. So number one, let's make sure we have the right number of sig figs, and number two, let's put a unit on it. So this is the concentration, so it's in molarity. So this will be molar. I'll put a capital M. If you want to write moles per liter, then feel free to go moles per liter. That works too. How many sig figs do I get? The pOH was 4.8. The number before the decimal doesn't count. The number after the decimal does count. So the 8 is the only significant digit on this. There is one significant digit, which means this is not going to be 1.58. This is going to be either a 1 or a 2. That's it, times 10 to the negative 5. Okay? Because this is a 5, I mean, there's controversy over the rule that you use. I'm going back to the old school. If it's a 5 or higher, you're rounding up, and if it's a 4 or lower, you're rounding down. So I'm going to this is going to be, with 1 sig fig, it's going to be 2 times 10 to the negative 5 molar. Okay, so if you've got a pH or a pOH, it's 10 to the power of negative value of that, and that's what the concentration is. And you have to be careful with how many sig figs did the pH or the pOH have on it, and then how many do I write on my concentration, because you're using a new rule and you're kind of going back and forth between your previous knowledge with the concentrations and your new knowledge here with the pH and the pOH. Okay, so that is just a couple of examples of kind of converting it back and forth, back and forth. Got to know your little formulas, and if you know your formulas and you can use your calculator, you should be good to go. So the next one is the relationship between pH and pOH. Remember I said earlier that you can go directly, if you have a hydronium, you can go directly to a pH, or you can go directly to a hydroxide concentration. You cannot go directly between the hydronium concentration and a pOH. You have to go one of the other ways and then indirectly get the pOH. So what is the relationship? Okay, well, you probably already figured out one. If I know a hydronium concentration, I can get a hydroxide concentration using the relationship of Kw. So Kw divided by your hydronium will give you hydroxide. Once you have a hydroxide concentration, you negative log that, and that's a pOH. That works, no problem. And go for it. Like, if that's what you want to do, that's what you want to do. But there's another relationship. You can go the other way. If you have a hydronium and you go to pH, you can then go from pH to pOH. There's a relationship between pH and pOH. And at 25 degrees, you're going to know that all the time. You're going to use it quite often, because oftentimes you're going to be given a pH of something, and rather than go pH to hydronium concentration, hydronium to hydroxide concentration, hydroxide to a pOH, it'd be way easier if you could just go quickly pH to pOH, if you knew what the relationship was. So I'm going to show you that relationship. So the relationship is based on water equilibrium's K expression. So Kw equals hydronium times hydroxide. And we start there. So what if, okay, this is a little bit of a mathematical thing. What if you decided, because we're using these negative log concepts, what if we took the negative log of both sides, right? So in math, you can do whatever you want. If you felt like square rooting both sides, you could if you wanted to. As long as you do the same thing to both sides, you're allowed to do whatever you want because they remain equal. So I'm going to take the negative log of both sides. So I'm going to take the negative log of this side equals the negative log of this side. Okay, cool. So for those of you who have you've done your logs in math class, and you figured out what is a logarithm, you know the log rules and all those kind of things. You kind of look at this right-hand side of the equation, and there's a log rule kind of pops out at your head. That if you're taking the log of two things multiplied together, you can take that equals the sum of the individual logs. Okay, so for those of you who haven't got Math 12 and you're going, what? Who cares? It doesn't matter. It doesn't matter. You will probably care about what results here at the end. So negative log of Kw, kind of the concept. Negative log, that's what the P means, like the little pH, pOH, pKw, that means negative log of. So if you have negative log of the Kw, that means pKw. pKw, the negative log of that. This guy right here, because it's hydronium times hydroxide, I can actually take the negative log of the hydronium, plus, and it's the log rule, plus the negative log of the hydroxide. Okay, so that's kind of weird right there, but that's the log rule. Negative log of the hydronium plus the negative log of the hydroxide equals the negative log of hydronium times hydroxide. Cool. Well, that complicated mess right there, negative log of hydronium means pH. Negative log of hydroxide means pOH. So if you kind of substitute pH and pOH for the negative log, complicated looking weird part of that, you get this very fundamental mathematical principle. Like, I haven't actually put any numbers in yet. I've just taken this K expression up here, which is a very general mathematical expression that applies to water at any temperature. I've taken the negative log of both sides. And lo and behold, you get this very simple logarithmic relationship between the two of them. pKw equals pH plus pOH. These two things right here, these two mathematical relationships are very critical. Those things have to stick in your head. You probably, hopefully, already have Kw equals hydronium times hydroxide. You can use that when you know what Kw is. Well, can you use this other one? Well, of course you can. So pKw is just the negative log of Kw. So if you happen to know Kw and you negative log it, well, that's what pKw is. It's just the negative log of that value. So let's take this an extra step. What if we're talking about at 25 degrees? At 25 degrees, which is kind of what, Chem 12 kind of works with 25 degrees all the time. So at 25 degrees, what is the value of Kw? Well, you know that. You've memorized it. It's already in your head. 1 times 10 to the negative 14. What if I negative log that guy? What if you negative log 1 times 10 to the negative 14? Well, okay, I'm going to do this in my head just to demonstrate kind of what the concept of the log is in a pH and a pOH and a pKw. 1 times 10 to the negative 14. The 1 times whatever, well, 1 times anything doesn't have any effect on it, right? So it just leaves you with 1 times 10 to the negative 14 really just means 10 to the negative 14. That's what it really means. Well, a pH, a pOH, a pKw, a P whatever means that it's just the exponent. Switch the sign. So 10 to the power of negative 14, well, we're talking about the pKw then is just 14. That's all it is 14. And have it in your head. pH and pOH at 25 degrees. It's critical. At 25 degrees. Always add up to 14. Like that's super simple. You know one of them, you always know the other one. So if I take the if I take the negative log of Kw at 25 degrees, I get 14. Now, how many sig figs are on it? We're going to use whatever sig figs are on our pH and our pOH value. So I'm typically going to be using 2 decimal places. You kind of use whatever you want. It's actually been determined kind of more sig figs than that, but kind of we'll go with 2. Equals the pH plus the pOH. So if they always have to add up to 14, if you know one, you always know the other. So if the pH is 5.1, well, 14 minus 5.1 is 8.9. The pOH is 8.9. If I know a solution, oh, I haven't got it up here on the board anymore. If I have a solution that has a pOH of 13.0, the pH is 1.0 because they have to add up to 14. And so you can apply that all you want. So there are going to be situations where you need one or the other. You calculate a hydroxide concentration. Later on, we're going to be doing kind of big, giant calculations. You're going to have a base and you're going to throw it into water. You're going to calculate how much hydroxide it makes. That will give you the pOH. Then you're going to go, well, what's the pH of that solution? Well, once you know the pOH, you subtract it from 14 and you've got the pH. Okay, so that relationship, these two relationships are always true at 25 degrees. You happen to know this is 1 times 10 to the negative 14, and this is 14. So you can apply those things all you want. If you happen to have water that's not at 25 degrees, oftentimes you can still use these mathematical principles to determine the value of kW. And so you can start to manipulate these little formulas for any temperature. They apply to any temperature. It just happens to be at 25. You know what that is, and you know what that is. And non-25, you don't know what they are, but you can still use the mathematical principles. Okay, so next class, we're actually going to start getting into how do you calculate the pH of a solution that you make, like in a lab. If I throw in 4 grams of hydrochloric acid into 300 milliliters of distilled water at 25 degrees, what's the pH? And so a lot of the acid-base unit is now taking these mathematical principles, what is an acid, what is a base, and now taking it a little bit deeper and trying to figure out a little bit more of what's going on. Trust me, it gets a lot more complicated, so we've got a lot more classes to go here, but it gets really quite interesting, actually. It's quite neat. Okay, so thanks a lot. We'll see you next time.